Okay, the last section in chapter 5 is about the selection rule. So harmonic oscillator selection rule is delta V equal to plus minus 1. So transition between harmonic oscillator state can occur only between adjacent energy levels. So let's try to understand this rule. So this can be understood based on the transition dipole moment. So we are going to take a look at why this property, the transition dipole moment, is related to the probability that the oscillator makes a transition from the specific state to another specific state in section 8.6. But now we just assume that this is the correct claim, correct statement. So we want to calculate the probability that the oscillator makes a transition from state B to B prime, and this is proportional to the square of the integral. Dipole moment operator here. So this is the transition dipole moment, and probability is proportional to the square of the transition dipole moment. So now we just assume that electromagnetic radiation is propagating in the g direction. So dipole moment operator has only g component. Okay. And we can expand the dipole moment operator. So in terms of x, starting from the base value, and we are going to add the first order correction and second, third, higher order correction is there. So mu 0, this should be the dipole moment. Dipole moment at the equilibrium geometry. And x is the displacement from the equilibrium geometry. So with this expansion, we can rewrite the transient dipole moment expression. And we are going to truncate the expansion for the dipole moment operator at the first order, because we can assume that the contribution from the higher order correction is not that much. Prime dx. So transient dipole moment is simply the sum of two components. The first term is and the second term is Okay. So you will easily realize that this term should be 0, right? So we now discuss the transition from B to B prime. That means B cannot be same as the B prime. So due to the orthogonality condition, this integral should be 0. And we only have the second term, right? So we need to calculate this integral. And we know that the wave function of the one-dimensional harmonic oscillator is normalization constant multiplied by the Hermite polynomial and exponential c squared over 2. And you know that x and c has the relation like this. So we are going to replace this integral with the explicit expression of the wave function. Then and we have the x, but now we want to replace the expression with c. So c over square root alpha, that is the expression for x, and b prime h Hermite polynomials of v prime's order right. So we now to group the constants, we now collect the constant term, this one, this one, this one, and this one, and this one. So it should be like nb prime over alpha hb c hb prime exponential minus alpha square, c square, and dc. So we need to evaluate this integral, and you know that if we have the Hermite polynomial multiplied by the Hermite polynomial multiplied by the polynomial equation, then we can reduce this expression with the sum of the Hermite polynomial with adjacent order. So based on the recursion formula, c multiplied by hb should be right. So that means this expression highlighted with the yellow line. So this should be hb prime v prime hv prime minus 1 half of the hv prime plus 1. So we are going to replace this yellow box with this expression. HB multiplied by B prime HB prime minus 1 like this. So they are just constant. That means we can just focus on the HB and multiplication between HB and HB prime minus 1, right? So B should be multiplied here. Exponential C squared DC right? We have the same constant here. So to have the non-zero value of transition dipole moment, we need at least one of these two terms should survive. And the only possible way to have non-zero value is B should be equal to V prime minus 1, or B should be equal to V prime plus 1. So that means B and V prime should be differ by only 1, plus 1 or minus 1, right? So the selection rule is defined based on transition dipole moment, right? So for the harmonic oscillator, the transition can only occur between the adjacent energy levels. And we also have to mention that so far we have discussed the non-vanishing value of this integral. But even though we have the non-vanishing value for this integral, what happens if this constant would be 0? So no matter this integral is 0 or not, if we have the 0 value for the lambda mu over lambda x, then it is just 0, right? So the first selection rule is the first condition for the transition in the vibrational motion is B should be B prime plus minus 1, and second rule is lambda mu over shouldn't be 0. This means at the equilibrium geometry, if we take the derivative of the dipole moment along the x direction, that should be 0. That should not be 0. So that means the dipole moment should change along the motion. Okay, so this is the second condition. Okay, so even though this is the expression for the one-dimensional harmonic oscillator, but you can easily extend this expression into three-dimensional expression, and the content would be same. So let's take a look at the example. Carbon dioxide example. Water first. So let's take a look at the water. So water has 3 degrees of freedom for vibrational motion. So the first one is the symmetry stretch like this. Symmetry stretch. And the bending motion. And the last one is the anti-symmetry stretch. So if you take a look at these 3 motions, then all these 3 motions involve the change in the dipole moment. So yes, all of them satisfy the condition, this one. So we can observe the transition between the adjacent energy levels in the vibrational spectroscopy for water. And all these modes are observable. Then what about the carbon dioxide? Carbon dioxide, we have the 4 vibration motion. And among them, the symmetry stretch of these 2 CO bonds, this doesn't really induce the change in dipole moment. So that means along this motion, there is no dipole moment change, then that means this is 0. So we cannot really observe this vibrational motion in infrared spectrum. Okay. Okay, so this is the end of the chapter 5, and the homework will be so please check the homework. Okay, thank you for joining me today, and see you next time.